Welcome back to IT 7014, Part 9. Today, we are looking at application architecture patterns. The way we structure an application acts as its physical mechanics. These architectural decisions set an absolute energy floor, a baseline of energy consumption below which no amount of clever code-level optimization can ever reach. How we divide our deployable units dictates exactly how much base network overhead and latency our system will generate before it performs a single useful task. We will analyze 4 specific structural families to map these physical trade-offs: monoliths, microservices, serverless functions, and event-driven queues. To evaluate these objectively, we have to look past cloud vendor marketing and measure the actual physical work generated by a single user request. This graphic outlines our main deployment options. On the left, monolithic architecture is a single deployable unit. Features share one database and communicate via instant in-memory calls. On the right, microservices split code into independent processes communicating over the network. Because of this structure, microservices always do more total work per request. Serializing data, transmitting it over a physical network, and parsing it on the receiving end is measurable physical work that a monolith simply does not have to do. Paying this network tax is justified only when different parts of the application have highly divergent scaling demands. If your recommendation engine requires 10 times the compute capacity of your user profile page, splitting allows you to scale the heavy feature independently without running excess copies. If your features experience uniform load, splitting them wastes infrastructure. For small teams with uniform traffic, a modular monolith, where code is strictly separated internally but deployed as a single unit, provides clean boundaries without the network penalty. Adding microservices without a strict scaling justification simply multiplies your baseline runtime footprint, actively increasing latency and total energy consumption. Serverless computing, or function as a service, pushes this division even further. The primary draw of serverless is the promise of zero idle costs. When there are no user requests, no infrastructure runs, and you consume zero baseline energy. This diagram exposes hidden mechanical costs. The top bar shows a cold start. Provisioning a container and initializing code consumes significant time and energy before execution begins. At the bottom, a warm invocation routes to an existing container, executing immediately without the startup penalty. Serverless runs most efficiently when traffic is bursty, unpredictable, and low on average. The heavy cold start penalty is paid once per burst, and you avoid powering an idle server during the long, quiet periods in between. Conversely, applying serverless to a workload with steady, continuous traffic is highly inefficient. At high, sustained rates, you repeatedly pay the per-invocation platform overhead, quickly eclipsing any energy savings you might have gained from stripping away the idle server. Serverless is an idle time optimization tool, not a universal upgrade. Misapplying it to steady traffic patterns generates massive, invisible energy waste. On the left, a synchronous architecture blocks the caller, forcing infrastructure to sit idle and consume power waiting. On the right, an event-driven flow uses a message queue. The client is released immediately, while independent consumers process the heavy work at their own pace. This structural buffer means you no longer need to provision servers to survive your maximum peak traffic. You size your infrastructure for the average load, drastically reducing the idle baseline footprint of the entire system. The cost of this pattern is delayed execution. It works perfectly for side effects like sending an email receipt or generating a background report. But during massive traffic spikes, the time it takes for those tasks to complete will stretch as the queue fills up. Decoupling the timing of a user's request from the execution of the back-end work is the single most effective way to eliminate peak infrastructure bloat. Let's test these principles on a physical system. We are building an appointment booking platform. It handles 30,000 bookings a day with steady daytime load, run by a small team of 6 engineers, and it requires heavy overnight reporting jobs. We built the core application as a modular monolith, avoiding microservice overhead. We route emails into an event-driven message queue, decoupling side effects so screens load instantly. Finally, overnight reporting is isolated into a serverless function, consuming zero compute during the long daytime idle period. Highly efficient architecture is never about selecting one universally superior pattern. It requires mapping specific component models directly to the physical shape of the demand. Let's apply this to the IT 7014 exam. Professor Faustino builds his test questions to see if you can spot the misapplication of architectural patterns based on industry hype. Take question 1. The prompt describes an application built as a single deployable unit, where internal calls are in-memory function invocations. That strict mechanical detail is the definitive identifier for a monolith. There is no network overhead. Question 2 tests your knowledge of serverless mechanics. The exam will throw fabricated buzzwords at you, like warm-up phase or container migration. Reject them. The sequence of allocating a container and loading a runtime is strictly defined as a cold start. Question 6 asks about an external consultant pushing to split a uniform application into 8 microservices. We know this is a trap. 8 separate runtimes carry 8 separate baseline footprints. For a uniform load, that operational overhead provides zero physical benefit. Question 11 presents a nightly batch job running for 40 minutes. Serverless fails here because platforms enforce hard execution time limits. And always-on server fails because it wastes 23 hours of idle power. The physics-based correct choice is a scheduled container that runs only for the duration of the work. To pass this module, you must analyze problems strictly through the lens of physical overhead and workload signature. You must completely ignore the broad industry trends. Mastering monoliths, microservices, serverless, and event-driven architecture simply means knowing exactly where code execution ends and network overhead begins. In Part 10, we will shift our focus from how components communicate to the actual data flowing inside the pipes. We will cover API design, payload efficiency, and the REST versus GraphQL debate. True digital intelligence requires ensuring that your system's shape is perfectly molded to the reality of its workload. See you in the next module.